Well, I spoke a bit about this with your colleague in the Netherlands, Eric Verlinde, and also Andy Strominger. But toward exploring the ADS CFT correspondence, which is what I hope to get to in this conversation, and which I understand is among the most important results in string theory, I'd like to begin by talking about holography or the holographic principle. And I know that this was its historical origin, but I think you agree that maybe discussing black holes and Bekenstein-Hawking radiation is maybe the best way to introduce the concept?
Right. So in the 70s, Bekenstein proposed that black holes have some entropy. And then Hawking discovered that black holes have a temperature. So, and they realized, and together with other researchers, they realized that black holes seem to obey the laws of thermodynamics. So it's a bit mysterious that this object that started out as some geometry of space-time unique geometry now behaves like a thermal object. And then there was a question that was raised, which was, where are the microstates of the black hole? So what do these formulas mean? So what the formulas mean, taken at sort of face value, is that the black hole can be viewed from the outside as a quantum system. So it's some system that has a finite entropy, so finite number of states. And you can make the hypothesis that it evolves according to some ordinary quantum mechanical laws, though they are not. Though these properties are not manifest from the gravity picture. From the gravity picture, all you can calculate is the entropy. So there was the idea that a better understanding of gravity would lead to an understanding of what the black hole, what these degrees of freedom of a black hole are, or a full description of a black hole. Now, this picture that I just told you is something that you might naively get from these formulas of thermodynamics, but it was not obvious, and in particular, people like Stephen Hawking disagree with this picture. So they were proposing that black holes actually destroy information, so they don't behave like an ordinary quantum mechanical object, but they fundamentally lose the information, at least from the point of view of an observer who stays outside the black hole. This is sometimes called the information problem. And so then, since string theory is a theory of quantum gravity, you can try to analyze this problem in string theory. The main technical breakthrough that made this possible was a discovery by Joe Polchinski of something called D-branes. I will not get into the details of what they are, but they are some other objects that string theory has. So string theory has these strings, but then it has these other objects. And they have two very important properties. One is that they're on the verge of becoming black holes. So they are, if you just take one or two of them, they behave like a very fundamental object, which is a very precise description. But if you take many of them, they start curving space and they start to behave more and more like black holes. So that's one point. And the second point is that, Polchinski gave a very precise description of the excitations of these objects, so how they interact among each other and with the fields outside. And so there are precise mathematical formulas that tell us how this happens. So roughly speaking, what happens is that on these objects, the excitations are described by certain theories that are similar to the theories that describe elementary particles, or in particular the strong interactions. But what's important for this is that they follow well-defined quantum mechanical rules. And so with these D-branes, you could define quite easily as so-called extremal black holes. So the simplest low energy system. If you take these D-branes at low energies, they have many properties in common, and you can view them in some limits as black holes. So extremal black holes are black holes that carry some charge. And so such black holes have a mass which is bigger than the charge. And as you lower the mass, the Hawking temperature becomes smaller and smaller. And when the mass is equal to the charge, they become a very cold object. So, but with still large entropy. And this large entropy was first derived and reproduced by Strominger and Baffa using precisely these rules of the D-branes. And then after that, a bunch of us started trying to understand what happens when the temperature is not exactly zero, so it's a little bit above zero. So there, you can have some more non-trivial dynamics. You can throw things into the black hole can evaporate, and so on. The idea is that what happens with these black holes is that they have a geometry which is flat space very far away. And then as you approach the black hole, they develop a long kind of throat or region where the gravitational potential becomes smaller and smaller. If you look at from the outside, those excitations look like they have lower and lower energy. And so it's a bit like a big gravitational well. And at the bottom of the well, you have the horizon, the black hole. So this ADS-CFT correspondence came by saying that this region of the well itself, plus the horizon and so on, can be described by these theories that describe D-branes at low energies that were standard quantum field theories or theories of interacting particles. The geometry of these throats is something called anti-de Sitter space. So it's a negatively curved space is very symmetric. It's one of the simplest negatively curved spaces you could have. So that's where sometimes it's called ADS. The anti came from the fact that the actual space that the sitter was a person who considered an expanding universe, and that's called the sitter space. It has positive cosmological constant. It has negative cosmological constant. That's where the word anti comes from. It's trying to explain the name of the space. But anyway, so it's some simple negatively curved space. And so the idea is that the physics in this space is the same as the theory of interacting quantum particles without gravity. So it translates a problem with gravity to a problem without gravity. In particular, in the problem with gravity, you could have a black hole. And then you can describe that black hole from this theory without gravity, and the black hole becomes just an ordinary thermal state, thermal system in this theory. So this allows you, in principle, so it's a conjecture that these two things are equal. It's a conjecture that passes many tests, and there's a lot of evidence for the conjecture. But if you assume this conjecture, then you would have a complete description of these black holes. So the cases that are best understood are cases with lots of symmetries that come from string theory, so in higher dimensions, and very, very idealized cases.
Mm-hmm. Well, that was a great overview, and I'd really like to get into many of the things you just described in more detail. And I'd like to start with the first question that you raised, which is, where are the microstates in a black hole? And one thing that I want to better understand with regard to black holes is, just because the information they contain can be read off as a sort of description from the event horizon, does this mean that the event horizon is all there really is? Because that's the sense I've gotten from some sources that I've read. And if I'm not mistaken, if my memory is not mistaken, Eric Verlin told me that he doesn't really even think about the singularity at the core of a black hole at all, which is where at least we uninitiated into string theory conceive of the information within a black hole residing.
Mm-hmm. Okay, so I think people sometimes say that the information is at the horizon because the entropy is proportional to the area of the horizon. But we don't have any very concrete mathematical theory where that is actually realized. So in ADS-CFT, what happens is that you have a black hole with its horizon, and it's within some bigger space. So there's some space that continues. And what ADS-CFT tells you is it replaces the black hole and the whole space all the way to very large distance by an alternative theory where that lives basically on the boundary in a sphere very far away, that contains interacting particles, and the black hole is some thermal state in that theory. So that's what we know with precise mathematical description. In that description, you cannot say that the degrees of freedom were at the horizon. In fact, you would also say they are at infinity. They are very far away. So in that sense, the description is very non-local, sometimes also called holographic. Well, it's holographic, where you're looking at it from very far away and you're describing this, three-dimensional space in terms of a theory that lives in the two-dimensional sphere far away. But maybe there is in the future people will understand the description where the horizon, you can localize the black hole degrees of freedom at the horizon, but we don't have it yet. So that's one point. The second point is that when we talk about these degrees of freedom, they are the degrees of freedom that describe the black hole as seen from the outside. Right? Now, you might be an observer that's falling into the black hole, right? So if you are falling into the black hole, general relativity predicts that you cross the horizon, you don't feel anything special at the horizon, and that you will then eventually get into the singularity. And maybe you'll die at the singularity. And we don't know exactly. So when we get to the singularity, the current techniques we have, including the ones from string theory, don't tell us exactly what will happen. And so that's something that is currently not understood. That's another question we don't understand in string theory. So through this string theory model, through holography, ADS-CFT, we can describe very nicely black holes as seen from the outside, but we haven't succeeded yet in understanding the black hole interior. There are various ideas people are pursuing, and hopefully will be understood. I think it's very important to understand the interior, because the interior is a region that looks a bit like it looks like a big crunch. So it's a region, the space-time inside the black hole sort of collapses into singularity. And so if we understood well the interior and the singularity in the future, we could perhaps time reverse that and understand the singularity in the beginning of the Big Bang. So the right. Questions are related somehow. Yeah, go ahead.
Yeah, one thing that I didn't really understand about Eric's views was that my understanding was the singularity at the center of the black hole is so important because that is precisely where the two theories, general relativity and quantum field theory, break down, because space in general relativity is smooth, but it becomes jittery and chaotic at that level.
Yes, no, that's correct, and I think we don't have an answer to this question. So string theory gives us answers to some questions, but we haven't understood this particular question. So you should view it as a theory under construction. There are many questions that we don't know how to understand, how to solve.
And this is just a terminological curiosity, but do you prefer not to use the word hologram or holography or the holographic principle?
No, yeah, we can use it. So this idea comes basically back to the Bekenstein formula, which says that the entropy of a black hole is proportional to the area rather than to the volume. And then this led to the idea that if you have a region of space, the maximal entropy you can fit in should be proportional to the area, not to the volume. Because otherwise, when we collapse it if we imagine collapsing into a black hole, we would not obey the second law of thermodynamics. And so this led to the idea, to Toft and Susskind, of thinking that you should have this kind of dimensional reduction in gravity, that you have a three-dimensional theory, three space dimensions, but if you take a sphere far away, you should be able to describe it in terms of, or any sphere, you should be able to describe it in terms of a theory that has a number of degrees of freedom, which is at most the area of the sphere. So that's the idea of holography. The ADS-CFT correspondence is a realization of this idea when you put that sphere very, very far away. People have made attempts of bringing the sphere not far away, but at more finite locations. And there are some ideas in that direction, but we don't have a precise mathematical description of that situation where you bring the sphere finite location.
The reason that I asked about the term hologram or holography is, and I couldn't tell if you preferred not to use it, and I thought that maybe this would be because it connotes, at least with some physicists and lay people, that the bulk of the universe or the black hole is in a sense illusory, and what really exists is this bounding surface, and maybe that was something that you resisted.
No, I think that the two descriptions should be viewed as equivalent, or
okay.
Sometimes it's called the duality, that the two are alternative descriptions, I think. Now, presently we understand better, so in this situation of ADS-CFT, we presently understand better the boundary theory. So this theory far away, we think it's completely well-defined. And we could do arbitrary computations, at least in principle. But the bulk theory, we don't understand it as well. As well as we understand the boundary theory. And so some people want to say that, or people often say that the space-time in the bulk is emergent. It's some kind of, by emergent I mean it's a property that would be true when you have a boundary theory with many degrees of freedom, but not when you have a small number of degrees of freedom. So similar to how, let's say, certain properties of matter are emergent. So if we talk about, let's say, the color of a piece of metal, that's a property of many atoms. But if you take just a single atom of iron, we will not have the same color, if you wish. So that, in this sense, there are many properties of physics of ordinary materials that depend on the fact of depend on having many atoms. So, for example, water can be a liquid or a gas, and those are two configurations which are distinct when you have many atoms. But if you had one atom, you couldn't, or one molecule of water, you couldn't tell whether it's one or the other. So there is the idea that space-time is like this, that only emerges when you have many. I think the idea is correct, but in the sense that if you want a classical space-time that looks like what we have in the space-time around us, then it's emergent in that sense. But the idea is that if you had a small number of particles, perhaps you would have a very quantum mechanical space-time. And so if you are wishing to say that you are tolerating a very quantum mechanical space-time, as I think we should in a theory of quantum gravity, then I think it is possible that we have a precise equivalence. But the problem is the bulk theory is not as well defined as the boundary theory. So far, if someone wants to say that the bulk theory only makes sense when we have a large number of particles on the boundary, then we can contradict that person. Maybe I should explain. There is a concept I referred to here that I didn't fully explain. So the idea is that these theories that live at the boundary consist of particles, and they are similar to the theories of particles that we use for nature, for describing nature, except that there are kind of many different types of particles. So there is some number n of particles, particle types, that is very large. They're somewhat similar to the theory of strong interactions. So in the theory of strong interactions, is a theory similar to the theory of both electromagnetism and weak interactions, but the particles have a property which is called color. This number of different types of color is 3 in the case of the theory of strong interactions. And so, for example, there are 3 types of quarks and so on. And in these theories that live at the boundary, you would need this number. There's a similar number, but it should be very, very large. So as large as the universe is in Planck units. So, for example, if you wanted to describe a universe that has the size of our universe, but let's say we had negative cosmological constant instead of positive, but with the same magnitude, then the number you would need is 10 to the 120. So it's a very large number.
Yeah. Well, I'd like to get back to conformal field theory and then anti-de Sitter space in a few minutes. But right now, returning to what you said about the equivalence of the bulk and boundary theories and descriptions in this duality here, restricting ourselves to black holes, you said that, the region of the well can be explained via a description of, I think, low energy D branes on the boundary, and that these are equivalent, but because the latter is lower dimensional and quantum mechanical and mathematically more tame, it's just easier and perhaps more useful to use this version for some reason because they're intertranslatable, but one is not fundamental.
That's right. It's more useful for questions about black holes and whether black holes preserve information or not. That's one application where the boundary description is more useful. There are other questions for which the bulk description is more useful. So, and that's a direction that's also been explored a lot. So for that, I need to say one more thing about this boundary theory, which is that the particles that live in this boundary theory are very strongly interacting. So they interact very, very much with each other. And this makes this boundary theories hard to analyze. But the bulk theory is somehow simpler to analyze, at least for certain problems. Like, let's say we don't consider problems involving black holes, but other problems involving gravity waves, or even with black holes, how gravity waves fall into a black hole and these type of questions. So those are questions we can easily answer using the Einstein equations. So the bulk gravity description. And so then this ADS CFT correspondence translates a difficult problem in the boundary theory to a simple problem in the bulk theory. So that's using this equivalence in a different direction. To learn there, what you're doing is you're using gravity to learn about strongly interacting theories. And you can use this to model systems in either nuclear physics or condensed matter physics and so on.